Hi, how are you?
Hi, sir. I'm good, and you?
Good. So we also live on YouTube, ne?
Okay.
Yeah. So we're going to do Richard Lee's principle. I'm happy, ne? But I'm not happy about the timing for this lesson. But this is one of my favorite topics, ne? Richard Lee's
Okay, sir.
principle. Okay. I'm just waiting for you, and I'm not sure if he's joining or what. But let me quickly check on him and see if he's joining the lesson.
Okay, sir.
Okay, so now which topic did you cover so far?
Okay. Just go over. This week I was very busy with maths. Like for my paper too.
Yes, for physics.
Okay, let me go to paper 2 so that I can show. Okay, so I was doing that ketones, that stuff,
Oh,
and
okay.
I was doing E E reduction reaction
Okay.
and
So you did like the organic chemistry, ne?
yes, I did that first part, yes.
Oh, okay, nice. You here? How are you?
Hi, sir.
You good?
I'm good, and you, sir?
I'm good. Thank you very much for joining. Tell me, did you do organic chemistry at school, or this is going? No, not organic chemistry. Uh, chemical equilibrium, or this is going to be your first time doing chemical equilibrium?
Yes, sir.
First time, ne?
Yes.
Okay, no problem. I'll try to make sure that I explain everything, ne?
Yes. Thank you.
Emihle, please forgive me for aiding you hand. I was supposed to have a session with him also today, ne? Yeah, I was saying please forgive me for aiding you hand, ne? Don't worry, tomorrow morning we continue as usual, ne?
Okay, sir, no problem.
I'm trying to share the screen, but I'm not winning, ne? Or should I just say the entire screen? Okay, can you please confirm if you can see my screen?
Yes.
Yes, sir.
Okay, but when I do it like this, can you see it like clearly? You don't see a lot of things now, you only see chemistry grade 12.
Yes, sir.
Yes.
You sure?
Yes.
Okay, so uh, on this lesson today, we're going to talk about like chemical equilibrium, ne?
Okay.
So I don't want us to waste any time. Let's start working on chemical equilibrium. So I know that Emisa, you already know chemical equilibrium, but we'll go through this together, ne? Step by step.
Yes, sir.
Yeah. I'm not going to assume that you guys know the chemical equilibrium, but I'll make sure that I explain everything on chemical equilibrium.
Okay.
do this. Right. So another thing, I'm not going to move fast today, né?
Okay, sir.
Yeah, because and I also want you remember Emi, so most I'll just communicate with you while Yuhan is learning. This is new to Yuhan, but already when you did this topic, right?
Yes.
Yeah, so I'm just gonna go through this with you, Emi, and I'll keep on asking you questions, okay?
How?
Yes.
How say hi, again?
You know these things again.
No, but like, hi, say.
Bo, so now tell me from that grade, the one that you did, tell me, do you still remember what is an open system when we talk about an open system? Do you still remember what is an open system?
No.
You don't remember what is an open system?
Mm-mm.
Okay, so an open system, this one, we say it's a system where in which both energy and matter, so it's a system in which both energy and matter can exchange between the system and its surrounding, né? Do you still remember that? Like system, it's a system in which both
energy and matter.
Yes, energy and matter. So energy and matter, they can what? They can be exchanged. They can be exchanged. So we're going to talk more about like the nodes. You guys are going to get a lot of nodes today, né?
Yeah.
Between the system and its surrounding. Yeah, so this is what we're going to do today. We're going to have like a lot of nodes, you know? So in chemical equilibrium, we have an open system and a closed system, which is something that I need you guys to understand. So a closed system, but before we talk about an open system, one thing I need you to understand about this one, an open system, né? The open system, this guy cannot reach equilibrium. That's one thing we need to understand. It cannot reach equilibrium. Only a closed system can reach equilibrium. So an open system cannot reach what? It cannot reach equilibrium.
Okay.
Are you happy with that?
Yes.
Okay. Right. Remember, this is going to be a very long lesson, né? So let's make sure that by the end of this lesson we've covered everything, né? So now when we talk about a closed system, remember, closed system, now I think you have the idea what is a closed system, okay?
Mm-hmm.
So a closed system, this is what we're going to talk about in this lesson. A closed system, it's a system which mass is conserved inside the system. So this one, this will be a system which mass, the mass is conserved. What do we mean when we say it's conserved inside the system? What do we mean by that? I hope you guys are taking notes, né?
Yes, sir.
It's conserved inside what? It's conserved inside the system. So when we say it's conserved inside the system, we are saying that okay, but even if the mass is conserved inside the system, just know that energy can enter or leave the system freely. So energy can enter or leave the system freely. So it can just go in and out. The energy can what? The energy can enter or leave the system what? Freely. Because only the mass will be conserved. Mass, or in an open system, both energy and matter can exchange between the surrounding, but in a closed system only the mass is conserved inside that system. The energy can enter or leave the system. I hope you guys understand that part, ne?
Yeah.
Right. This one, a closed system, is the one that can reach equilibrium. This one, it can reach equilibrium. I hope you understand that part, ne?
Yes, sir.
Okay. So a system which does not contain a gas does not have to be sealed to be a closed system, ne? So let's talk about what we say reversible reaction. Do you know we're going to talk about that one? But tell me, are you guys happy differentiating between an open system and a closed system?
Yes.
So now, this is a task for you. I need you to go and consult your exam guideline. Ask your exam guideline how to define a closed system, because when I check in most of the exams, they want you to explain what we mean by a closed system. In most, they just want a closed system. But please make sure that you know how to define these two definitions according to your exam guideline, okay? So now, Emily, tell me, what do we have an exam guideline?
Why do we have it?
Yeah, why do we have it? What is the purpose of exam guideline?
It's basically to guide us through what is gonna go, like what the exams are about.
Okay, that's nice. But now let's talk about the definition. Why should we define according to the exam guideline?
Because it gives you what the marker wants.
Exactly. Exactly. What the marker wants. Because each and every learner must have the same definition, so that they don't do like favors and say, this is close, man, let me give this learner 2 marks. You see, that's why we have an exam guideline. Make sure that all your definitions, you take them from the exam guideline, not from your textbook. I hope you understand that, ne?
Yes.
So now, you have a question?
Yes, sir.
Okay. Okay, let's talk about reversible reactions. Right. So when we say a reaction is reversible, just know that a reaction is reversible if the products can be converted back to the reactants. Okay? So let's say that we have 3 moles of hydrogen and they react with nitrogen. Okay?
Okay.
So now let's say this is in gas state. I'll definitely write those, and then I'm just gonna write something like this, and we produce 2 NH3. Okay, so now let's say this is in gaseous state, this is also in gaseous state, this is definitely also in gaseous state. So now let's say they tell you that delta H here is less than 0. They'll definitely tell you the heat delta H. So let's say we are given that delta H is less than 0. So in order for you to understand this, you need to revise what? You need to revise rates of reaction. But don't worry, because I'm here to assist you, I'll make sure that by the end of this lesson, you understand everything. Okay?
Yes.
So now, a reversible reaction, we say, a reaction is reversible if the products can be converted back to reactants. So, reversible reaction, we're going to represent them by these arrows. Can you see these 2 arrows?
Mm-hmm.
Once you see these 2 arrows, just know that these double arrows, they tell you that this is reversible.
Mm-hmm.
Are you happy about that? Johan?
Yes, sir.
Since this is new to you now, I think you understand what is a reversible reaction. Reversible reaction, it's reversible if the products can be converted back to the reactant. So this tells you that this NH3, we can take it back and we can form the product. This product we can form, this reactant we can form the product. You understand? So this arrow here, this will be your forward reaction. Okay?
Yes.
And this will be your reverse reaction. Right. So now, another important thing that you need to understand on this is to know, remember we have exothermic and we have endothermic, okay? You need to understand if the forward reaction is endothermic or the forward reaction is exothermic. You need to understand if the reverse reaction is endothermic or the reverse reaction is exothermic. So I just want to test you, Mister. Tell me which one is exothermic, which one is endothermic. I just want you to give it a try.
Like what does so mean? Like which reaction is?
Yes, remember we have the forward reaction, which is this one, and we have the reverse reaction with this one, and we are given that delta H is less than 0. So now, is the forward reaction endothermic or exothermic?
Because I put him on the spot. Is the forward reaction exothermic or endothermic?
Yes.
I am just trying, eh?
Yes.
But
That's what I need you to try, because you know one thing about learning, obviously you can't just wake up and know everything. That's why we say you are learning, you are practicing. Why? So that you can master these things. You can't just wake up and say, you know what, I know that forward is what. You see, we need to practice.
okay, sir. So I am gonna say it's endothermic.
Why are you saying it's endothermic? Why is forward reaction endothermic?
I took it because isn't the exothermic where delta H is less than 0?
Is it? Say that again.
Exothermic is when delta H is less than 0.
Exothermic.
Yes.
Okay, let's write this down. So you are saying that if delta H is less than 0, the reaction is what? The reaction is exothermic.
Yes.
I agree with you on that. Exothermic. So, exothermic. Now, I really agree with you on that. But now look at this. This one will be endothermic. Now.
Yes.
If you haven't done rates of reactions, don't worry, everything will make sense. Nah? Where what I need you to understand now is that if the heat of reaction is negative, less than 0 means negative, our reaction we're going to say exothermic. So maybe after this lesson you can go through and understand the difference. But for now, I just want you to know when do we say exothermic and when do we say endothermic. So exothermic is when delta H is less than 0, and exothermic is when delta H is less than 0, and endothermic is when delta H is greater than 0. Okay?
Okay, so it's my science thing again.
Yes. So now look at this. Look at this. Delta H is less than 0, and what I'm going to teach you today, each and every listen, eh? Listen. How can I say this, nah? Are you listening?
Yes, I'm listening.
Listen. Irreversible reaction, nah? Irreversible reaction. What I need you to understand is that the change in enthalpy that is given. Should I write this down?
Yes.
Okay. Irreversible reaction. Let's write this down. In reversible reaction. I want you to understand that the change in enthalpy, the change in enthalpy. So when we say the change in enthalpy, we are referring to delta H. Ne?
Yes.
That is given. The one that is given. Always note that the one that is given is for what? Is for the forward reaction. The one that is given is for forward reaction. Always, ne?
Yes.
You understand that?
Mm-hmm.
So now tell me, what will be the forward
Yes,
reaction?
The forward reaction will be exothermic.
Thank you very much. So in a reversible reaction, the change in enthalpy that is given, it's always for forward reaction. So this tells us that the forward reaction, look at this, you see this arrow here, it represents the forward. So it's going to be what? It's going to be exo. So this will be your exo. And then this arrow that is going in that side is the reverse, and this will be your endo. You understand? Your endo.
Yes.
So now we know that reverse it's endothermic, and we have the forward as exothermic. Tell me that you have the best tutor. Exothermic. And that's it. So now you understand how this works, ne? I don't want us to have problems when we get to answering the dynamic chemical equilibrium, ne?
Okay.
Are you happy with that? You understand when do we say this is the reverse reaction? Okay. I'm listening. Wanna say something? Emily?
No, sir. I didn't say anything.
Okay. So now that you guys understand that, let's talk about the dynamic chemical equilibrium.
Dynamic chemical equilibrium.
Yes.
That's the first time.
Come on. I think, the dynamic chemical equilibrium, ne? You'll understand what is this. You always know this thing, because you guys always say it's chemical equilibrium. It's dynamic chemical equilibrium, ne?
Mm-hmm.
Right. In this one, what I need you to know is that when a system reaches dynamic equilibrium, so when a system is in dynamic equilibrium, just know that the forward and the reverse reaction are taking place at the same rate.
Sorry, sir. I'm just gonna go back to the previous notes. Shouldn't we also include the OT, like what is exothermic and what endothermic is? Like exo, the release of heat, where endo is the opposite.
Oh, you mean like if it absorbs energy, what?
Yeah, shouldn't we? Is that not important?
For chemical equilibrium, it's not important. That's why I'm saying to you, Hen, that you don't have to worry about this, né? So you can stress about this when you do rates of reaction. For now, I just want you to know that the forward reaction, it will be for the change of enthalpy that is given, né? And then if the forward reaction is exothermic, just know that the reverse is endothermic, né?
Okay, sir.
Right. So back to dynamic chemical equilibrium. In dynamic chemical equilibrium, I need you to understand that the forward reverse reaction are taking place at the same rate. So what we are saying is that the forward, so in this guy, the forward and the reverse, they will do what? We're saying that are taking place at the same rate. Tell me, you still don't know what is dynamic chemical equilibrium. after giving you the statement?
No, maybe if you start doing it.
Okay, no problem. So now, let's say that you have a graph like this, né? You are in an exam. This is what you are given, and then let's say we have something like this. Oh, now you have the idea, né? I know.
Yeah. Okay.
Okay, so let's say you have something like this, né?
Okay.
And then let's say you have another one like this. Okay, so you know what I need you to note. Let's say this one, just know that the one that starts at 0, this is 0, and then let's say that both of them, they will say, let's say this side you'll have the amount. Remember when we talk about the amount, we are referring to what? The number of moles, né?
Okay.
We are referring to moles. So this will be the moles. So now, if we look at this, né, I'm going to say that, look at this. Now, the number of moles for the number of moles, let's say this starts at 10, né? This starts at 10. The number of moles, how many? I'm just gonna give you something. Let me write down. Let's go back to this. Let's rewrite this equation down, né? Guys, chemistry, there's too much information, so please, I need you guys to be patient with me, né? Because we're going to write a lot of things here on the board.
Okay, sir.
Okay, this reacts with N2, and then gas. And please, Emily, expect a lot of questions from me, né? That's that's my way to train you.
But what if I don't know?
It's okay.
Especially this one. This one.
But you know, by the end of this lesson, you're going to understand. Now tell me, you don't understand how the reversible reaction works. You understand, right?
Yeah.
You understand everything that we discussed again?
Yes.
Yeah. So now this is NH3, né? Then it's in gas state. So now let me check this. Tell me how many the number of I need you to tell me something, né? I need to know the number of, what is this? I need to know the number of moles that we are starting with on the reactants. I want you to try and tell me how many number of moles. Look at the equation. This equation is balanced. Now tell me, how many number of moles do we have? For the reactants, if you add all the number of moles for the reactants, how many do we have? I just want to see if you know how to count the number of moles. Because you see, at this point, this is where the reactants start. Remember, on the reactant, we're going to start with something. Then the reactants will reduce because we're going to use the reactants to create what? The products. So now even the graph is telling you that the products start at 0, then we are producing the products. That's why the number of moles for product start increasing from 0. You understand? So the reactants, they are the one that will decrease in number of moles. The products, they are the one that will increase. So this tells you that this one is NH3. And this one is going to be, so this one, looking at this NH2, so we don't have much of NH2, so we're not going to use much. So this one is the one that will be on top. And this one will be the H2. You understand that part? Okay, now to count the number of moles of reactants, first thing first, tell me, how many hydrogens do we have? So how many hydrogens is 3 times 2, which is 6. So we have 6 hydrogens. And what about the number of, we have 3 times 2 is 6. And then what about nitrogen? How many do we have? 2, right?
Mm-hmm.
We have 2. So we have 6 plus 2.
Which is 8.
which is 8. So are you saying that the number of moles is going to be 8 for the product, for the reactants? Oh shucks. There's still we still have to learn that. So look at this. The number of hydrogens. The number of hydrogens, we have the initial amount moles of hydrogens that is reacted with what? The initial amount of nitrogen. So they will start from this point, then they will decrease, and then we can see that somewhere here we're going to create two. We're going to produce 2 of ammonia. So this is, we're just gonna put the 2 somewhere there, and then when I check this side, we can put maybe that 8 or 10, whatever that we have there. So then to show that this is going to decrease. So it's fine. For now, the only thing that we are talking about here is the dynamic chemical equilibrium. So look at this point here. Can you see that this point going that side all the way here, can you see that the forward and the reverse reaction are taking place at the same rate? That is what that is why the dynamic chemical equilibrium is saying. Can you see that this is the same rate? This is the same rate that we are referring to. You understand? Are you still with me? So if I call this T1, they will ask you in an exam, at T1, what is going on at T1? You're going to tell them at T1, the reverse and the forward are taking place at the same rate, or you can say that the system reaches what? Equilibrium. Are you happy about that?
Yes.
Right. So now what I need you to understand is that when the system reaches equilibrium, that amount of the amount of ammonia, remember ammonia is our product, it's NH3, So when the system reaches equilibrium, just know that the amount of ammonia, hydrogen, nitrogen remain constant. As you can see, it will remain constant. It remains constant. All these three, they remain constant. Do you understand that part? You saying
I'm saying yes.
Oh, okay. You stay with us.
Yes, sir.
Right. So this graph here, we call it what? You can call it this. Look at this amount, and this time is time. So let's say we need to draw the graph using the rate of reaction. The rate. So let's say I have my graph like this, and then remember this is my time, and then this side I'm going to have the rate. So let's say I need to use the rate. So now when I use the rate, I can just say this is the product. They start from 0, pure, and then let's not indicate with an arrow. This is my reactants. They start from 0. They don't start from 0, then Q. So then, can you see that they will move at the same rate, this part? So this one, when you use the rate, this is how you draw. But when you use the number of moles, this is how the graph will look like. So now, this tells you that at this point here, this is your T1. This is where the reverse and the forward reaction are taking place at the same rate. So at equilibrium, the amount of concentration of reactants and products are constant. We are not saying they are equal. Please pay attention to that. Ne?
Okay.
At equilibrium, you see, at equilibrium, the amount, and when we are talking about the amount, what are we referring to? The concentration, okay?
Yeah.
So we are saying that the concentration of reactants, and products are constant. Guys, When we say of reactants and product, when we say constant, we are not saying they are equal. Are constant. Don't say equal, ne? They remain the same. Constant, not equal. Constant does not mean this does not mean equal. Okay?
Okay.
We are not saying they are equal. Are you guys happy about that?
Yeah.
You can. Now you understand, eh?
Yes, sir.
Are you happy?
Getting there.
Yeah, don't worry. Don't worry, I got you.
Yes, sir.
Nice. So now you know what I'm going to do now. We're going to talk about this guy. I love Lee-Chatterley's principle. Ne? So I'm just gonna let's talk about Lee-Chatterley's principle. So you see Lee-Chatterley's principle. This is what we're going to use to answer some of the exam questions. Ne? Because most of the questions they need you to understand this. Trust me. I just believe that this is one of the concept of or the law that most learners they find it difficult to apply. This guy, the Lee-Chatterley's principle, or Lee-Chatterley's. You see my pen, Lee-Chatterley's principle. My pen is not doing well, guys. So this principle, it says that when an external stress, Amy said you have stress.
Stress.
Hmm?
Yes, I do have stress.
Tell me it's about books.
Yes, it is about books.
Because they say boys before books bring babies, ne? I don't remember what they say. What is that thing? What are they saying, you had?
They say books before boys because boys bring babies.
Oh yes, you even know what I'm trying to say, ne? External. When an external stress. So when an external stress, when we say about the external stress, we are talking about the change in pressure, the change in concentration, the change in pressure. If you change pressure, you are causing us a stress. If you change temperature, or bakela stress, and we need to prevent that stress. Temperature. When you change the temperature, or bakela stress, when you change concentration, or bakela stress. So if you change one of these, if the external stress, when an external stress is applied, ne? Meaning that you change one of those things, it's applied to a system, ne?
Okay.
What happens? Guys, my SP pen is not doing well. I'm not sure what's the issue. What should we do? Okay. It's applied to what? Let's say it is applied to a system, ne? In dynamic chemical equilibrium. A system in dynamic chemical equilibrium. What will happen? So, hey guys.
No pain.
Yes. Okay, so listen. When an external stress, which we are referring to, a change, I'm not sure if you guys can give me a second to look for another one. But I know that when the issue is with the whatever that I'm using to teach. So the issue with this whiteboard, it's not the pen. Yes, the issue is with the whiteboard, not the pen. When it starts acting up. Okay, I can't find another one. Let's work. So now it says that the equilibrium I'm going to move slow, you see.
Yeah.
The equilibrium point in such a way as to do what? It needs to counteract or to counteract whatever the stress, to counteract the stress. Let's just put it like that. When you'll take the one from your exam guideline. Eh? So now, this is the Lichartlis principle. When an external stress, like a change in pressure, temperature, concentration is applied to a system, to a system in dynamic equilibrium, the equilibrium point in such a way as to counteract the stress. So tell me, how do you understand what is this? What is the Lichartlis principle saying? Because I think this is where we need to start.
I think my understanding is that if there is change within pressure, temperature, concentration within the system, then the system will react differently.
Exactly. The system reacts differently to whatever that you changed. So, but now before we go into Lichartlis principle, let's talk about describing the change in chemical equilibrium according to Lichartlis principle. Now, so according to Lichartlis principle, number one, you need to identify the external stress. So identify, guys, why is this doing this to us? Let's do this now, guys. I know even if we change, it's not gonna. Okay, so first thing first. Okay.
Identify external stress.
Yes. Can you guys see?
I can see, sir.
Okay, so
you must talk while writing because it's better.
Oh, okay. So first thing first, identify the external stress, né?
Yes.
So this will be the external stress. Remember, we are referring to the change in pressure, temperature, and concentration, né? Then you're going to state the system response according to Lichartlis principle. That's the first thing, né? You're going to state the what? You're going to state the system response. How the system will respond. The system respond. Right. So the system respond according to what? According as. Did you guys even pray today?
Today?
Yeah.
Well, I'm gonna be honest, I didn't yet.
Yeah, no, I see. Whoever that is witching you guys, while we do so, this topic is difficult. We need to pay attention. Lichartlis principle, ne?
Yes.
I even make wrong spelling error here. But
so
it's
you
fine.
Maybe you can just
talk
like
only.
say, and I'll write.
Eh?
I'll write what you're saying.
No.
stressing you now.
Let me do this, né? Just give me a second. Let's do this. Even if I change the bot, I thought we might. This might do well. What should we do? Okay, let me state the last one, né?
Okay.
Okay. I don't know what to do. So let's just continue. State which reaction after number 2. You're going to state which reaction is favored, ne? Just give me a second. Let me just do this, ne? You still there? Yuhan, how? Where's Yuhan?
I think he left.
It's not in the lesson. That's only you. Okay, let's we set number 1. Let's see if this one will work, ne?
Yeah.
Number 1.
Identify the stress.
Yeah, we're going to identify the stress, ne? I'm very sorry about that, ne?
It's okay, sir.
It's okay, sir. Nice, thank you. I know you always favor me, ne?
Yeah, boy.
Okay, so number 1, identify the stress. Number 2, we're going to do what?
We're going to state the system response according to Le Chatelier's principle.
Exactly, the system. You state the system response, ne?
Yes.
The system response according to what?
Le Chatelier's principle.
According to Le Chatelier's. So we're going to write more of this word today. Principle. That's number 2, ne?
Yes.
Okay. So number 3, what do we do on number 3? We state which reaction is favored, ne?
Yes, sir.
Listen. You see, if you follow all this step, which reaction is favored? Which reaction is favored? And you also have to talk the result. Tell us the result, ne? The result. The result of change of the system, ne? Or to the equilibrium, or you can just say to the equilibrium, ne?
Okay, sir.
Okay, so now once we have all this, ne, let's talk about the factors which affect equilibrium position. Do you know those factors? No. We mentioned those factors today on this session.
Okay, wait, let me think. The factors that affect?
The equilibrium position.
Oh, the equilibrium position.
Yes. The stress.
Oh, which factors which affect the equilibrium position?
Yes.
We said most it's gonna be temperature, pressure, or concentration.
Exactly. So it's 1, temperature.
Yes.
Number 2, pressure. And number 3, concentration. So now we're going to explain how each and every this factor affect equilibrium. Ne?
Okay.
Now we are starting with the lesson. According to me, now we just started with the lesson. We are done now. Let's start with pressure first. Ne? Number one, pressure. Let's talk about pressure. Ne? So I'm not gonna write everything. Ne? I'm just gonna explain how this works. So what I need you to understand on pressure is that pressure is for only gases. Ne?
Okay.
It will affect only gases. Okay? Only for, let's say, only for gases. So let's talk about pressure. What happens if the pressure increases? I'm going to give you what we call a code. But this code that we're going to create, in fact, let's create our own code, because if I give you the one that I used to do at high school, maybe you might be more like, you won't like it, or it's too much. Trust me, it's too much. But let's make this thing. Let's say P for pressure, T for temperature, C for concentration. Are you happy about that?
Yes, sir.
So now we are saying that we're going to denote the temperature by using T, the pressure by using P, the concentration by C. Ne?
Yes.
And then we're going to use increase and decrease. So increase, we're going to use arrow like this, going up. Ne?
Okay.
Decrease, we're going to use an arrow going down. You know why? Because I don't want you to have a lot of nodes. Simple thing. Ne?
Yes,
So the pressure, which is P, increase. Ne? So the pressure increase. So if the pressure of the system is increased, what happens to the volume of the container? So V for volume, ne? The volume will decrease. You understand? Because pressure is inversely proportional to volume. So the volume will decrease. Do you understand that statement?
Okay, so when pressure increases, the volume decreases.
Yes. So remember, the arrows up is telling you that pressure increases. Down is telling you that the volume decreases. Ne? I'm going to simplify this for you. I'm going to make this to be more easy. I'm going to make these notes for you so that you can understand them better. Ne?
Okay.
Nice. So we are saying that if the pressure of the system is increased, the volume of the container decrease. Ne? Is decreased. You understand?
Mm-hmm.
So the system will favor the reaction that produce less molecules of gas. Not making sense, ne? Not yet, again. Right. So let's put this down. If this, how can we put this?
Like an example.
No, not yet. Not an example yet. I need to find a way that we can use to put this statement, because I don't want to write everything down. So the system will favor the reaction. Okay, the system will favor the reaction that produce less molecules. Okay, so
I
eh?
have no idea.
Bone, Emil. Listen, ne? Listen. So, let me do this. Listen. We are saying that if the pressure is increased, what happens to the volume?
It decreases.
Thank you. And then the system favor the reaction that produce less molecule. So now look at this. I have 3 hydrogens. Now you only consider the number on front, the number of molecules. So it's 3, and then this one is 1. So that's 3 plus 1. That's 3 plus 1, which is 4. So the reactant, we have 4 molecules, and then the product is just 2, okay?
Okay.
So we are saying that if the pressure is increased, the system will favor the reaction that produces less molecule. So look at this. The forward reaction gives us 2. The reverse reaction gives us 4. And according to Le-Chatelet's principle, the system needs to favor the reaction that produces less number of molecules. So the forward is the one that is giving 2, and the reverse gives us 4. So this tells us that the forward reaction is favored. Are you happy about that? Do you understand how this works?
Yes, I understand that.
You sure?
Yes.
So the reason to reduce that pressure is PIVD.
Please decrease.
Yeah, so P pressure increase, volume decrease, again. And then the system favor the reaction that create what? Of the system is increased, the endothermic reaction is favored, and if the temperature of the system is decreased, the exothermic reaction is favored to heat up the system. So now let's do some example. Let's say we take water, né?
Okay.
And then this water, it's in gas state. Let's say it reacts with carbon dioxide. Plus, is the forward reaction exo or endothermic reaction?
The forward reaction.
Yes.
It's endothermic.
Exactly. The forward LP is endo. So this tells us that the forward, which is F, is going to be endothermic. So this will be endo. And then the reverse, which is R, this will be what? This will be exo. Are you happy about that?
Yes.
So now, if the temperature is increased, we are increasing the temperature. What will happen according to Le-Chatelet's principle? Remember, Le-Chatelet's principle says that an increase in temperature, we need to favor endothermic. So this tells you that according to Le-Chatelet's principle, the system will favor what? The forward endothermic reaction to reduce the temperature. You understand? So forward reaction is favored if we increase temperature. Now tell me, what will happen if the temperature is decreased?
The reverse reaction is favored.
Exactly. So you're going to say if the temperature is decreased, the reverse reaction is favored. Why? Because we need to, the reverse is favored to increase the temperature. Okay?
Yes.
Oh. Like, I need your attention on this, ne?
Okay, sir.
Oh, sure. Eminently. Emihle, ne?
Yes, sir.
Listen. I want you to understand this, ne? I need you.
Okay.
I don't want to lose you on what I'm about to say now, ne? Listen.
Okay.
The temperature is increased. I want you to move with me. The temperature is increased. Then when I tell me if the temperature is increased, which reaction is favored?
Endothermic reaction.
Is it the forward or the reverse?
The forward reaction.
The forward reaction. So this tells you that if the forward reaction is favored, we're going to produce more of what? Of this, right?
Yes.
So this tells you that the concentration of the products will increase. You understand?
Yes.
And then why? Because we are using more of the reactants to create more products. So this tells you that the concentration of the reactants will do what? They will increase. Do you understand that part?
Yes, I understand.
Then the concentration of the product increase, the concentration of the reactant will decrease. So now in an exam, they might ask you, they'll try to say, listen, they will say that what happens if the temperature is increased? Listen, are you listening?
Mm-hmm.
The temperature is increased, and the question is asking, how will this affect the concentration of the products? That will be their question.
Yeah.
Do you want us to write that question down?
Yes, we can write it down, sir.
Okay. So they say if the temperature is increased, how will this affect the concentration of reactants? Let's say reactants, né? And
Of
then
reactants, okay.
yeah, and then you know what they'll say? They'll say increase, decrease, or remain the same. You need to choose the correct one, né?
Oh, yeah.
Yeah, they'll say increase,
Decrease or remain the same.
decrease, or remain the same. And this will be like maybe 1 mark to choose, né? And then the next question, number 2, the next question they'll say use Le Chatelet's principle. Le Chatelet's principle to explain your answer in 1 point something, né? To explain your answer. And this question is 4 marks. So the explanation most of the time in chemistry is 3 marks. To choose here, it's 1 mark. You get me? Let's answer this question together, né? Let's answer this question together. So what I need us to do is that if the temperature is increased, né, how will this affect the concentration of reactants? Increase, decrease, or remain the same? So what I need you to do first is you follow the steps, né? You're going to write your code down. You are in an exam. You're gonna write your code down and say TIEN. The temperature is increased, so endothermic is favored. Okay? So if the endothermic is favored, the forward reaction is favored. Right? You understand? So if the forward reaction is favored, so this tells us that we're going to use more of the product, of the reactants we're going to use the reactants to create what? To create more product. So this tells us that the concentration of product increase and the concentration of reactants decrease because we're going to use the reactants. So the correct answer here is what? The correct answer is decrease. So the concentration of the reactants decrease. Then to explain this using Le Chatelet's principle, you're going to say that an increase in temperature favors endothermic reaction. The forward reaction is favored. And since the forward reaction is favored, more of the reactants are used. The reactants are used to create what? More products. Therefore, the concentration of the reactants decreases. Is this making sense?
Yeah, that made so much sense.
Are you happy about that? You good?
I'm good, sir.
Do you want us to stop here or you want us to keep going? What time is it? Let me quickly check the time first. I think even if we can... We started 4:30, ne?
4:30, yeah.
So we did 1 hour 30 minutes.
Yeah.
Okay, just give me a second. I just wanna check something because we still have concentration to do. Then Congratulations, you understand all the factors. I think you can also go to past papers, but I'll only give you the ones that I need you to work on.
Okay.
Yeah.
That's nice.
Yeah, I'll only give you the ones that I want you to work on. So for now, let's work on concentration.
Cool.
Yeah. Remember we did temperature, we did pressure. Now we're going to do concentration.
But sir, isn't concentration what we just did now?
No, you see, that's how they play with you, ne? So the concentration, you're going to see how this works, ne? So the temperature, you just have, so the concentration, just note that if the forward reaction is favored, the concentration of reactants decreases. But if they don't, they might not include the temperature, and then how are you going to, let's say they just tell you that concentration of the reactants is increased. How are you going to answer that? Because they don't include temperature. So you need to understand that if they include temperature, how to answer it. But if they only ask it based on concentration only, how to ask it. So this temperature, it also affects the chemical equilibrium. You understand?
Okay, yeah, that's a good one.
Yeah, you see. So now let's talk about the concentration. So you know this one is very, very, very different, but let's try to go through it now.
Okay.
Concentration. Okay, so if the concentration of reactants or product is increased, so if we increase product or reactants, just know that the equilibrium will change to counteract what? The stress and decrease the product or reactant, which the system is what? The system which was added on the system. I'm just going to give you an example on this one.
Okay.
Let's say that we increase, okay, it's fine. Let me do this now. So increasing concentration of product or reactants. Let's say that we increase, remember I is for increase, ne?
Yes.
We increase what? We increase concentration or we increase what? Increase concentration. Okay, let's call this ICA. ICR. Increase in concentration of the reactant or an increase in concentration of the products. Ne?
Oh, okay.
Right. So now, let's say that the concentration of the reactants. So let's call this the concentration of the reactants. So this is CR, then it's increased. We use an arrow, ne? Ne?
Okay, so.
Are you with me?
Yeah.
Right. So if the concentration of the reactants is increased, the forward reaction is favored. I'm going to explain that. So this favors what? This is F. F for forward reaction. So the forward reaction is favored. I think, man, are you happy with us using the codes, or you want us to write everything on the board?
No, sir, I like the codes.
Yo, I was praying that you say that. Yo, writing everything on the board. No. That's not a good idea. So, concentration of reactants increase, the forward reaction is favored, ne?
Yeah.
Let me explain this. Barikimang. Emission, look at this, ne? Let's go back to that bone. This guy here, these are my reactants, again. These are my reactants. So, if I increase the concentration of this or of that, any concentration of the reactant, if I increase it, according to Le-Chatelet's principle, it will favor the reaction that reduces whatever that we increased. So if we put more reactants, according to Le-Chatelet's principle, he's going to favor the forward reaction to do what? To use up whatever that we increased to create more product. You understand?
Okay.
Is this making sense?
Yes.
So this tells you that if we increase the concentration of the products, according to Le Chatelet's principle, we're going to want to use up whatever that we increased to create more reactants.
Yes. So reverse reaction favors that.
Exactly. So this tells you that the concentration of the products decrease, which reaction is favored?
The reverse reaction.
Exactly. The R is yeah. So now this tells you that if we talk about the decrease in concentration of the reactants or the decrease in concentration of the product. So what happened? If the concentration of the reactant, if the CR is decreased, which reaction is favored? Let me hear this from you. We are decreasing what? The concentration of reactants. Tell me which one is favored.
We are decreasing the concentration of the reactants.
Yeah, so the concentration of the reactants is decreased.
So, wait, so let me get it into my mind.
Think about it, ne? We are decreasing the concentration of the reactants. Which reaction is favored, forward or reverse? I think we can do this all day, ne? Because they are easy, like it's easy stuff, man. Look at this, ne? I'm saying that Le Chatelet's principle will want to decrease whatever that we are increasing. Le Chatelet's principle will want to increase whatever that we decrease, will want to decrease whatever that we increase. Now we are decreasing what? We're saying that the concentration of reactants, we decrease them. What will happen? Which reaction is favored?
The reverse reaction.
Thank you very much. Why? Because if we decrease the concentration of reactants, the Le Chatelet's principle will want to increase those concentration of reactants. So the reverse reaction is favored so that we can create more reactants. When you decrease reactants, Le Chatelet's principle wants to add more. So to add more, we need to favor the reverse reaction to use up the product and create more reactants. Is that making sense?
Yeah.
Tell me now you are enjoying the chemical equilibrium. So
I am.
Yeah. So this one we are saying that the reverse reaction is favored, and if the concentration of the products are decreased, let's look at this. We are decreasing what? The concentration of products. So this tells you that the forward reaction will be favored to create more of whatever that we are decreasing.
Yes.
It makes sense, ne?
Yes, sir, it does. It really does.
Nice. And that's it for the concentration. You see how concentration works?
Concentration is easy.
It's easy, ne?
Yeah.
It's easy. Let's see, what should we do now? I just want to check something. Let's leave everything that we. Okay. So please tell me you happy now?
Yes, I'm super happy.
Should we do one more example, or we just leave this like this and then I'll give you something to go through, ne?
Yes, please. I think I'd love that because I still wanna get the gist of this, go over it, study it and stuff. Yes.
Oh, okay. And please don't forget to record the number of hours that we did. So today it's 1 hour 30 minutes, ne?
Okay.
Right, and that's it from me. Thank you very much for attending. Tomorrow we're going to continue with this one, ne? Tomorrow we're going to continue with this one. Tomorrow morning, I'll see you tomorrow morning, ne?
Okay, but just send the stuff today, okay, so that I can
Should I send you examples
Yeah.
on what we did today, ne?
Yes, on just what we
Then
did
you
today.
can read the question and the answers, ne? But please
Yes.
don't forget the notes, those codes, ne?
Okay, sir.
Sharp, sharp. Thank you very much.
Okay, sharp. Bye, sir.
Thank you.